For this part of the video, we'll look at electric potential, not electric potential energy, just the potential, which is how much energy you have per coulomb of charge. That's pretty much what it means. The amount of work done that you need to bring a positive charge to that field. Here is a field right now. This is a positive charge in the middle. This is Q. He has a field pointing outwards. And if I had another test charge sitting right here, just chilling, and I will bring him closer. I will push him, push. He does not want to come. I need to do some work. So there is some energy required, okay? And depending on what his charge is, in this case it's a proton, I will divide that work by how much coulombs of charge that we have. So I know what my potential will be. I know what I will need to use. So I am going from A to B, for example. There will be two different potentials. I have a potential at A and a different potential at B. The closer I get, the higher my potential will be. So if I was to have like this here, and then I had this here, and let's say this was 12 volts, and let's say this was 0 volts, and we had a field line. The closer I get to the 12, the more potential is. The more I get to the right, the less potential I have. Same idea. This will stretch all the way to infinity. Eventually you'll get to 0. But here this might be plus 1,000, 1 million. It could be 12 volts here. It could be anything really. The potential here could be very high. And that means I will have to use that when I'm moving a charge closer to it. It depends on the charge that is causing it. I am not going to include the charge on the test charge. We're going to assume that there is nothing. We're only interested in the main charge, the field that he is in. This charge is sitting inside his field. So he will feel a force from him. He will have an energy from him. He is working on his different potential levels or potential lines, depending on what radius I choose to use. Okay, so the field, the potential will get closer. That means you will get a stronger potential as I get closer to it. We can use the rule like I mentioned, V equals U over Q, or the work done over Q. This rule stays the same. This is again just W equals QV from before. You would have done this before when you were doing charges and electricity. Work done is Q times V. It's the same rule that we're applying now in grade 12. So if you want to find the potential, simply use this rule. Whatever energy that he would have, divide by the charge itself. If I had 100 joules of energy and I had 2 coulombs of charge, the potential there is 50. That's, in this case, will be volts. That's just a quick mini example there for you. And electric potential difference is when I change the potential energy. I will move the charge between the 2 points. Like I mentioned, if I had a B and then I had A, this is B, I'm quickly drawing it, this is A, and I move between them, I move closer, I am now doing work, I am having to move it closer, I can calculate the energy change, I can do all that. It will be the difference between whatever potential this is. Let's say this was 10 volts, and this was 5 volts. The difference between them, yeah? In this case it would be 5. So that is really important to know. VB minus VA, or I should actually easily say V final minus V initial. That's the better way to say it. Final minus initial, or the change in work or the change in energy divided by Q, which is the charge. So we can see that the electric potential is always decreasing in the direction of the field. So if the field, this is a positive charge, the field line is going out. You can see that this field, this is 10 volts, this is 5 volts. Further away I get will be 3 volts, 2 volts, 1, and so on. It will decrease the further away I get from the positive charge. Very nice. Formula right here, V final minus V initial. Checking this out, a proton will move towards the negative charge. So if he moves that way, we'll do minus 2, minus 10, which means he lost 12 volts. That makes sense because he wants to be here. The positive charge wants to be here, so he will lose potential. So that makes sense. Easy peasy. So negative potential difference, as we've mentioned, there's another example, between 10 to 6. We will take the positive charge and we will move him down towards the negative charge. So I will do final minus initial, 6 minus 10, negative 4. He lost 4 volts coming down. And if it was the other way around, if I take this positive charge and I moved him up, what you'll do is final minus initial, in this case 10 minus 6 again, and this time it will be positive 4. He gained 4 volts of potential, which makes sense because he wants to repel. He does not like these positive charges. He will repel by them. He will need more energy, which is why the potential has increased. So potential is basically like voltage, potential energy is energy, funnily enough. Okay, however, if I had a point where I was sitting and I moved along and my radius didn't change, if I stayed in this area with my radius being the no change, you will find that there will be no work done. It's easy because there is no change in potential. I am not getting closer, I am not getting further, I am staying in my same line, which means on an equipotential surface, the potential is equal. So if I had 10 volts here, this whole thing is 10 volts. This whole line is 10 volts. I did not change it. If I do V finals minus V initial, it'll be 10 minus 10, you'll end up with 0. 0 work done. No work done on an equipotential line. So if I used parallel plates, as I drew earlier for you, it's uniform in the center, but not in the side. So we will ignore the sides. All our calculations will be assuming here somewhere in the middle. That's what we will do. So the distance we would say is D. So from here to here, we will call it D. And this is going to help us really get a new formula. We already know V final minus V initial. If I know that, that is nice and easy. For example, or that could be VI, that could be VF. I can call it 10 volts. I can call it 5 volts. It doesn't matter what's going on if I have it. However, I might not have it. I can find it by using the VED formula. V equals ED. The electric field is the change in potential divided by the distance. So I can just call it VED. And of course, QV. These are the 3 formulas you will want when you see parallel plates like this. We will use these 3 formulas in this situation.